Discrete mathematics comes in many shapes and sizes, and if you checked out 10 different college courses on the subject, you'd probably find 10 very different syllabi. But the one topic that all 10 courses would certainly contain is combinatorics, the mathematics of counting. So, here's a simple question. How many ways can you pick 5 numbers from 1 to 10? Now, there are a lot of different ways to answer that question depending on 2 missing pieces of information. Does order matter? And can you repeat numbers? So if order matters and repetition is allowed, then we call that a sequence. For example, when creating a 5-digit computer password, we're choosing 5 numbers from the set of digits 0 through 9. The order definitely matters, since the password 31415 is not the same as the password 31451. And since we're allowed to repeat digits, passwords would be an example of a sequence, because we can repeat and order matters. For example, okay, what if we were looking at a situation where order matters but repetition is not allowed? Then we call that an arrangement. So for example, if we were given 10 cards, ace through 10 say, and we had to deal 5 of them in front of us, okay, just take 5 cards here at random, then if the order, then repetition is not allowed because I can only pick each card once. And if order still matters, like in the game of 5-card stud, the order in which those cards come down typically matters, then ace 2, 3, 5, 8 would not be the same as 2, 3, 5, 8 ace. Okay? This would be an example of an arrangement. Here's another arrangement. Given that I have 5 cards in front of me, how many different ways can I arrange them? That would be another arrangement problem. Or for instance, if you were watching a horse race, we might care about which 3 horses finish first, second, and third, and so the order would matter to us. The next situation, if repetition is not allowed but order doesn't matter, then we call that a subset or a combination. Now, a combination is a fundamental concept in combinatorics, as you could imagine. For example, if all that matters is which 5 cards are dealt to me, but the order doesn't matter, it doesn't matter in which order I get those 5 cards, it's all the same hand to me, then this would be an example of a subset or a combination. Or if we had a barn full of horses, we might decide which 3 of them get to go out and play in the meadow. That would be a combination. There's a 4th situation that we'll talk about later where order doesn't matter and repetition is allowed. But to come up with answers to these questions, we need some basic rules of counting. We'll begin with the rule of thumb that I like to call the rule of sum. If an action is performed by making A choices or B other choices, then it can be performed A plus B ways. So for example, if I own 4 short sleeve shirts or 6 long sleeve shirts, okay, and no shirt is considered short and long, then the number of shirts that I could wear would be 4 plus 6, which is 10. We'll give a more precise definition of the rule of sum in a future lecture using the language of sets, but this basic idea is good enough for now. The other fundamental rule is called the rule of product, which says that if an action can be performed by making A choices followed by B choices, then it can be performed A times B ways. So for example, I have 10 shirts, and if I owned 8 pair of pants, and I obviously don't care about color coordination, then the number of possible outfits for me would be 10 times 8. For each shirt, I have 8 choices for pants. Here's a smaller example. Suppose that a label consists of a letter A, B, or C, followed by a number from the set 1 through 5. Then how many labels are possible? We have 3 choices for the letter, followed by 5 choices for the number, so the rule of product would tell us that we have 3 times 5, 15 possible labels. I've listed all the labels here for you to see. They fit inside of a nice 3 by 5 box. That's how we get 15. Or here's an example we'll see plenty of in this course, cards in a deck. Right? So we know that every card has a value that ranges from ace to king. You can think of those as the numbers 1 through 13. And a suit, either spade, hearts, diamonds, or clubs. So the number of possible cards is 13 times 4. 13 choices for the value and then 4 choices for the suit. That's 52 different cards in a deck. Some might consider this so basic as to be the very definition of multiplication. Here's an important example that will show up several times in this course. How many binary sequences, how many binary code words have length n? Okay, so when n is 3, we've seen that there are 8 code words, 8 words that you can make using zeros and ones. So where does the number 8 come from? Here, for each digit, we have 2 choices. 0 or 1 for the first digit, then 0 or 1 for the second digit, then 0 or 1 for the third digit. And if we have an n-digit word, we have 2 choices, then 2 choices, 2 choices, n times, giving us 2 to the n possible words or sequences. 2 to the n, as I've said before, is a very important number in combinatorics. In fact, it's our first important function in combinatorics. We'll see powers of other numbers appearing in this course too, not just 2 to the n. We'll see 3 to the n, 5 to the n, 10 to the n, but 2 to the n probably arises in the most natural contexts. All right, here's another combinatorics question. How many 5-digit zip codes are possible? Now, what's a zip code? It's 5 numbers, 5 digits, each between 0 and 9. So we have 10 choices for the first digit, then 10 choices for the second, 10 for the third, 10 for the fourth, 10 for the fifth. Multiply those together. That gives us 10 to the fifth, 100,000 possibilities. And of course that's the right answer, 100,000, because if you think of a zip code, they could range from as low as all zeros all the way up to all nines. And all nines would look like 99,999. Therefore, there are 100,000 possible zip codes. Not that they're all in use. Next question. How many zip codes have only odd digits in them? Like my zip code in Claremont, California is 91711. All of those are odd digits. Why don't you take a guess at the answer first before I just give it to you? Think about it for a second. Pause me if you'd like. Okay. And now, what did you get as the answer? How many use only odd digits? We have, to be all odd, we'd have 5 choices for the first digit, right? 1, 3, 5, 7, or 9. 5 choices for the second, for the third, for the fourth, and for the fifth. And therefore, there would be 5 to the fifth, 3,125 possible all odd zip codes. Next question. How many 5-digit zip codes use at least one even digit? So a zip code like 90210 has at least one even digit. Again, you might want to guess your answer first. Go ahead, take a minute or two, and think about what you think the answer should be. It's easy to overcount this problem, and don't be ashamed if you did, and to come up with an answer like 250,000. Now that answer can't be right. We know it can't be right because we just saw that there were only 100,000 zip codes possible, so you couldn't have 250,000 of them that had at least one even digit. Now fortunately, there's a correct approach that breaks the problem into 5 cases. How many use exactly one even digit, how many use exactly 2 even digits, and so on. But we're not yet ready for that approach. It uses the number n choose k, which we'll mention later in this lecture. Fortunately, there is a simpler solution. It's called the strategy of complements, which says, answer the opposite question. Our question was, how many zip codes have at least 1 even digit? To do that, we count all the zip codes and subtract those that contain all odd digits. And we know that there are 100,000 possible zip codes, and we can subtract off all 5 to the 5th, all 3,125 ways that use all odd zip codes, we worked that one out earlier, to give us 96,875 zip codes with at least 1 even digit. Next, we'll try some arrangement problems where no repetition is allowed, like how many 5-digit zip codes have all different digits? Well, there'd be 10 choices for the first digit. Then once we made that choice, now there'd only be 9 choices for the second digit. And once we made that choice, there'd only be 8 choices for the next digit, then 7, then 6. Multiply those numbers together to get 30,240 zip codes that use all different digits. As a sanity test, we see that's less than the 100,000 possible zip codes. Okay, but now suppose we expand from 5-digit zip codes to 10-digit zip codes. Then how many zip codes would there be? This time we would multiply all the numbers from 10 all the way down to 1. 10 times 9 times 8 all the way down to 1. We know that's the number 3,628,800, or at least we can calculate that. And we have a shorthand for that number. We call that 10 factorial. An ordered list where every object appears exactly once is sometimes called a permutation. Some textbooks refer to any sequence without repetition as a permutation, but most mathematicians don't. We'll just call those situations arrangements. So, this is, by the way, one of the 3 most important numbers in combinatorics. So along with 2 to the n, in the Combinatorics Hall of Fame belongs the number n factorial. And there's another number that we'll meet real soon. So just remember, n factorial is important. Its official definition is n times n minus 1 times n minus 2 all the way down to 1. N factorial is, if you want to memorize anything, what does n factorial mean? When you see n factorial, think of it as the number of ways to arrange n different objects where order matters. So if I have 5 cards and I'm asking how many different ways can I arrange them where the order matters, that's 5 factorial, or 120. Now, in Lecture 1, we saw that 2 to the n grows pretty quickly, but n factorial grows even faster. Here's a comparison of the first 10 numbers, 2 to the n and n factorial, as n goes from 1 to 10. You see, both of them grow pretty quickly. N factorial grows even faster. N factorial can also be defined recursively, that is, in terms of smaller factorials. For example, 5 factorial is, by its definition, 5 times 4 times 3 times 2 times 1, but the 4 times 3 times 2 times 1 is itself a factorial. So we have 5 times 4 factorial. In general, for any number greater than or equal to 1, we can say that n factorial is n times n minus 1 factorial. Notice that when n is 1, this formula says 1 factorial is 1 times 0 factorial. And in order for this to be true, in order for 1 factorial to be 1, we're going to have to define 0 factorial to be 1. Also, defining 0 factorial to be 1 is better for all our formulas to work out appropriately. Factorials also allow us to answer arrangement problems more compactly. So for instance, when we were counting those 5-digit zip codes with different digits, the answer 10 times 9 times 8 times 7 times 6 could be simplified and written as 10 factorial divided by 5 factorial. Now, the third most important number in combinatorics is pronounced n choose k, and it looks like this. Other names and notation for n choose k, you will hear them referred to as binomial coefficients. And other notation, though we won't use them in this course, I've seen CNK written in various forms, where the C stands for the word choices or combinations. Now here's the informal definition for n choose k. All right, this is the way I think about it. N choose k is the number of ways to choose k objects from n distinct objects where the order is not important and repetition is not allowed. So for instance, if I have 10 cards here, then 10 choose 5 would be the number of ways that I could take 5 cards out of these 10 where the order doesn't matter. Or if I took the entire deck of 52 cards, the number of ways that I could take any 5 of them would be 52 choose 5. 10 choose 3 is the number of ways to create a committee of size 3 from a class of 10 students. Or it's the number of ways if you had a barn full of, let's say, 10 horses, to choose 3 of them to go out and play in the meadow. That could be done 10 choose 3 ways. Notice that our numbers get smaller as we add restrictions. For example, the number of 3-digit zip codes would be 10 to the third, or 1,000. And if all the numbers had to be different, just like, say, the first, second, and third horse to finish in a 10-horse race, the answer would be 10 times 9 times 8. That's 720, which is less than 1,000. And if order doesn't matter at all, then the number will be even smaller. How much smaller? As we'll see, by a factor of 3 factorial, by a factor of 6. Okay, now here's the formal definition for n choose k. N choose k is officially defined to be the number of subsets of the set 1 through n with size k. So we met subsets in lecture 1. 4 choose 2, for example, would count the size 2 subsets of the set 1 through 4. Here are the size 2 subsets of 1 through 4. Those are we've seen those before. Those are 6 of them. And so therefore 4 choose 2 is 6. So for example, by the formal definition, 10 choose 3 is the number of ways to pick 3 numbers from 1 through 10 where order doesn't matter. So I'll pick, say, 2, 7, and 8, which, by the way, would be the same as picking 2, 8, and 7. 10 choose 3 would also be the number of length 10 binary words, words consisting of zeros and 1, where the number 1 occurs exactly 3 times. And therefore the number 0 occurs 7 times. Like here's a length 10 binary word with 3 ones. Why are there 10 choose 3 of them? At first it might seem like, hey, doesn't order matter in this problem? Well, the order matters in terms of the sequence, but how many of them have exactly 3 ones? All we have to do is choose which 3 positions contain the ones. So here we've chosen positions 2, 7, and 8. That's the same as choosing the positions 2, 8, and 7. So there are 10 choose 3 such words. By the way, when I think of binomial coefficients, I'm reminded of a story from a recent visit I took when I was speaking at another college. And I was being given a tour of the campus, and one of the mathematicians said to me, pointed to one of the buildings, and he said, "We call that the binomial cafeteria." I said, "Oh, is it because they offer so many choices?" And he said, No, it's because you should buy no meal here." By the way, you may wonder where the word buy in binomial comes from. It comes from the fact that when creating a subset of a set, every entry has 2 possibilities. Either that entry is in the subset or it's not in the subset. Or in our binary words of length n, each digit has 2 possibilities. It's either a 0 or a 1. Okay, so if n choose k is so important, we should have a formula for what it is. So here it is. I'm going to present it to you. I'm normally not an advocate of memorizing formulas, but this one occurs so often, and I don't want you to have to go through the derivation each time. It's okay to memorize this formula. For any number k between 0 and n choose k is equal to n factorial divided by k factorial times n minus k factorial. So for example, 10 choose 3 is 10 factorial over 3 factorial times 7 factorial. And since the 10 factorial over 7 factorial, there's some cancellation going on there, that's equal to 10 times 9 times 8. We can calculate that as 720 divided by 6, or 120. So that's the formula, but why does it work? I'll answer this in sort of an indirect way. First, let me ask you an easier question. Okay, imagine I have a classroom with 10 students and I have 10 chairs, and 3 of those chairs are in the first row and 7 of those chairs are in the second row. And I ask you, how many ways can those 10 different students sit among those 10 different chairs? Well, that question's easy. There are 10 factorial ways to do that, because the first student has 10 choices, then the second student has 9 choices, and the third student has 8 choices, and so on. The fact that there was a first row and a second row didn't matter to answer it this way. But let's answer it a second way. Let's first decide who sits in the front. Then we'll arrange the people in the front. Then we'll arrange the people in the back. So how many ways can I choose which 3 people get to sit in front? 10 choose 3. Once I've chosen that those 3 students are going to sit in the front, they can be arranged how many ways? 3 factorial ways. And what about the people in the back? How many ways can those 7 people be arranged? 7 factorial ways. So by the rule of product, we have 10 choose 3 times 3 factorial times 7 factorial ways for all the students to be seated. Now I've just given you 2 different answers to that question. Which answer is right? Well, our logic was impeccable both ways. Therefore, both answers are right. On the one hand, the answer is 10 factorial. On the other hand, it's 10 choose 3 times 3 factorial, 7 factorial. And since both answers were right, we can set them equal to each other. And when we do, we get 10 choose 3 equals 10 factorial over 3 factorial times 7 factorial. And the same logic will give you the general formula for n choose k. So it makes sense to look at certain specific values of k. So for instance, when k is 0, you'll notice that n choose 0 would give us n factorial over 0 factorial n factorial. And since 0 factorial is 1, we just get an answer of 1, which makes sense because there's exactly one way to choose 0 objects out of n. All right, now let's actually play some cards here. Let's use this to analyze some poker hands. Starting with the question, how many ways can you pick 5 cards out of 52? How many 5-card poker hands are there? We've already said the answer to that is 52 choose 5, but now we have an actual formula that will allow us to calculate it to be 2,598,960. But what we might really be interested in are questions like, okay, so how many full houses do I have? A full house consists of 3 of one value and 2 of the other. Like we might have 3 queens and 2 sevens. That would be a full house. So how many full houses are there? Well, let's create a full house. First, I have to choose which value gets tripled. I've got how many choices for the tripled value? 13. It could be any card value from ace to king. In my mind, I like to make a definite choice now. Okay, I've chosen queens. Okay, once I've decided that, how many choices do I have for the next card value, the card value that gets duplicated? Well, there are now 12 choices. In my mind, I'm thinking something like sevens. Okay, now that I've decided it's going to be queens and sevens, I have to decide which queens and which sevens. How many ways can I choose 3 queens out of the 4 possibilities? by definition, 4 choose 3. And how many ways can I choose which 2 sevens? 4 choose 2. And since 4 choose 3 is numerically equal to 4, and 4 choose 2 is equal to 6, when I multiply those numbers together, I get 3,744. So if you wanted the probability of being dealt a full house right off the top of the deck, the chances of that happening among all the roughly 2.6 million poker hands, about 3,700 of them are full houses. So 3,700 over 2.6 million is about 1 in 700 is your chance of getting a full house. All right, here's another question. How many ways are there to get exactly one pair? So this time we choose which cards are going to be paired up. Let's say aces. So I've got 13 choices for the paired value, let's say for aces. And then I decide which aces, which 2 aces out of the 4 am I going to have? Well, there are 4 choose 2 ways to do that. Then we have to decide, here's the tricky part, then we have to decide which 3 other card values. All right, let's say you decided to go with 2, 3, and 5. How many ways can you decide on those 3 other card values? It's not 12 times 11 times 10, because that would put some order into the problem. Instead, it's 12 choose 3. So I've chosen, I'm going to use 2s, 3s, and 5s. And then once you've chosen those, you then have to assign suits to each of those cards. There's 4 choices for the 2, 4 choices for the 3, 4 choices for the 5. Multiply now all these numbers together, 13 times 4 choose 2 times 12 choose 3 times 4 cubed, and you get 1,098,240. When you divide that by the total number of poker hands, about 2.6 million, then you get the probability of getting exactly one pair is 0.42. All right, here's another poker problem. How many straights are there? And for those of you card players out there, I'm including straight flushes in this calculation. So a straight would be something like 9, 10, Jack, Queen, King. 5 consecutive card values in a row. Okay? That can be as low as ace through 5, 1, 2, 3, 4, 5, as high as 10 through ace, 10, Jack, Queen, King, ace. So there are 10 types of straights. And that's the first number in my calculation. That's the bottom card of the straight. Once I've chosen the bottom card, I know what the other 4 values are. Then I have to assign suits to those cards. And there's 4 choices for the 10, 4 choices for the first card, 4 choices for the next card, and so on. 4 to the 5th ways of assigning suits. That's a little over 10,000 ways of doing it. The probability then of getting a straight is going to be 10,240 divided by our 2.6 million. That's about 1 in 250 chance, about 0.4% chance of being dealt a straight. Here's another question. How many flushes are there? A flush is 5 cards of the same suit, like say the 2, 3, 5, 8, and King of Hearts. That would be an example of a flush. And again, I'm going to include straight flushes in this calculation. So how many ways can that happen? Well, there are, from the first decide what suit is going to be on every card. There are 4 choices for that suit. Once you've chosen that, you now have 13 cards, let's say all the hearts, the ace of hearts through the king of hearts, to choose 5 cards for your hand. And that can be done 13 choose 5 ways. So the total number of ways of doing it is 4 times 13 choose 5. That's a little over 5,000. And the probability then of getting a flush is about 1 in 500. By the way, if we compare that to the probability of getting a straight, which was about 1 in 250, we see that flushes are rarer, and that's why they're more valuable in the game of poker. Now, I remember when I was counting poker hands in one of my discrete mathematics classes years ago, and I would take requests. I'd say, go ahead, throw out a poker hand, we'll try and count it. And somebody said, okay, how many poker hands are garbage? No pairs, no straights, no flushes. Okay, so I said, well, let's try it. Let's first consider hands that don't have any pairs in them. Okay, no repeated values. So how many ways could we do that? So, well, we have to have 5 different card values and that out of 13. So there's 13 choose 5 ways to pick which 5 different values we're going to use. Let's say 2, 3, 5, 8, and king. Once we've chosen that, we can assign suits 4 to the 5th different ways. But we've overcounted. That answer is too big. So we have to subtract off those poker hands that were straights, right? Because we don't want any straights. We've calculated the number of straights. There are 10 times 4 to the 5th of those. And we've also have to subtract off those hands that were flushes, right? So all these hands that have no pairs in them, they might have been straights, they might have been flushes. So I have to subtract off those flushes, 13 choose 5 times 4 different flushes. But now I have to add back. Now that straight flush issue is going to come back to haunt me, because anything that was a straight and a flush, these are called straight flushes, got subtracted off twice. So I need to add those back in order to get the correct answer. How many straight flushes are there? There are 10 types of straights. And once I've chosen that I'm going to use a certain kind of straight, like 3, 4, 5, 6, 7, then there's only 4 choices for the suits. Choose the suit of the first card, 4 choices. Everything else, there's just 1 choice. So there's our answer. 13 choose 5 times 4 to the 5th minus 10 times 4 to the 5th minus 13 choose 5 times 4 plus 10 times 4. Slightly over, about 1.3 million, slightly more than a half. Now, a student of mine pointed out, he said, that your answer looks interesting because it factors. You could algebraically factor that as 13 choose 5 minus 10 times 4 to the 5th minus 4. Why is that? Is that a coincidence? And I said, there are no coincidences in combinatorics. There has to be a good reason why. Let's see why that is. So in order to count that, we'd say, well, first choose any 5 values out of 13. How many ways can we do that? 13 choose 5 minus 10. 13 choose 5. But I have to subtract from that 10 ways for those 10 ways that are straights. I'm not allowed to have a straight. So there's 13 choose 5 minus 10 ways to pick my card values. Then I can assign suits practically however I want. If I had no restrictions, there'd be 4 to the 5th ways of doing it. But since they can't all be the same suit, since I can't have a flush, the answer, I have to multiply it by 4 to the 5th minus 4. Let's summarize. Let's recount what we've learned so far. From a collection of n distinct objects, how many ways can you select k of them under the following assumptions? For sequences, when order matters and repetition is allowed, we came up with the answer of n to the k. For arrangements, where order matters and repetition is not allowed, we came up with the answer of n factorial over n minus k factorial. And in the case of subsets, where order does not matter and repetition is not allowed, we came up with our answer n choose k, n factorial over k factorial times n minus k factorial. It's the number of subsets or combinations. What if order does not matter and repetition is allowed? These are called multi-subsets, and we'll discuss them in Lecture 5. We'll consider this problem and many more variations in future lectures. In fact, in our next lecture, we'll step back to get an overview of all the types of counting problems whose 12 types are organized into what is sometimes called the 12-fold way of combinatorics. To see how this all unfolds, please join me for the next lecture.